Good morning. My name is Jonathan Rathsam, and I'm from NASA Langley Research Center in Hampton, Virginia. It's my honor this morning to introduce our next keynote speaker, Peter Coen. Peter is the Mission Integration Manager for NASA's Quests mission, and he is responsible for ensuring that NASA delivers representative data to support international efforts to develop standards to certify low-noise commercial supersonic aircraft. Most of Peter's 40-year career at NASA has focused on supersonic flight. For the past 2 decades, he has been the NASA focal point for supersonic technology development. And prior to his current role, he managed NASA's Commercial Supersonic Technology Project for over a decade. Peter holds a Bachelor of Science degree in Aerospace Engineering from Polytechnic Institute of New York and a Master of Science degree from the George Washington University. Peter is an avid runner, a hockey fan, and a private pilot who has amassed 30 seconds of supersonic flight time. It also impresses me personally that Peter can name any aircraft he sees. Please join me in welcoming Peter Coen to deliver the next keynote.
Okay, good morning, everybody. Now for something completely different. Really excited to lead the team that's working on the mission. That's our quest to achieve quiet supersonic flight. Quest is our brand because it is a quest, and the 2 S's for supersonic. It's the culmination of many years of research and dedication by a great team that, like I say, I'm happy to represent. So I'm going to give you a little bit of background on how we got started, where this comes from, talk a little bit in detail about the different phases of the mission, things that are going on now and things that come in the future, talk about how we're going to use this data to interact with the international community, on the idea of actually creating this standard for acceptable levels of sound for some supersonic flight. Wouldn't be data works without talking about a few data challenges and then a few concluding remarks. And that's our brand. Okay, so NASA invests in aeronautical technologies that can result in a future air transportation system that is transformative, global, and sustainable. And no one can argue that getting there twice as fast would be both beneficial from a transformation in terms of air travel and for global aviation. But the question is how to do it sustainably, how to do it without environmental impact, particularly from various noise sources. Sonic boom is one of them. If we're going to be global, you have to be able to operate supersonic aircraft not just over water, but over land, as airline operations would be. So NASA views that the current restrictions on supersonic overland flight are a key barrier that needs to be overcome. We work in a community of interest in supersonics that includes research agencies, companies, regulators, and academia. And the vision of that community is that supersonic travel can be made accessible to a broad spectrum of the traveling public. But we can only do that if we have environmental impact that is compatible with the future of a future aviation system that is sustainable for global use. That's kind of the background why NASA has chose to look at supersonic flight and focus on sonic boom among the many environmental challenges that supersonic flight faces. And to overcome that barrier, the Quest mission is really the culmination of our activities that we're engaged in to overcome that barrier for supersonic flight. So in order to do that, we need to replace a ban on supersonic flight, which, by the way, 50 years ago tomorrow was the enaction of the U.S. ban on supersonic flight. So it's timely to take a new look at it. But to create this new standard, we need proof that we have a design method that actually works. We can actually impact the sound in a meaningful way. And to do that, we need data. We need to understand how people respond to that. And despite the fact that in the lead up to the ban on supersonic flight, there was a lot of community research done on understanding the impact of sonic boom, that sound was so unacceptable and clearly out of the bounds of what could have ever be considered acceptable, that data is not relevant to really getting to understand what level might be acceptable. So we need community data from a large, diverse community. And of course, it's a U.S. ban, but supersonic flight is a global thing. So we can't work this alone. It has to be done with the cooperation of and interaction with the international community, because the standard needs to be accepted internationally. So, like I say, this is what Quest is all about: is essentially collecting and delivering data to the international regulatory community that they can use in their work, which is ongoing, to develop a new certification standard for acceptable levels of supersonic en route noise. So, how do we do that? This is 40 years of research condensed onto one slide. But essentially, you've got an airplane flying at supersonic speeds. It creates a system of shock waves, which eventually coalesce as they travel to the ground. They pile up on one another, and you're left with two signals, which are very intense and very abrupt, which causes disturbance to people on the ground. So the idea is to modify that flow field so that you don't get the piling up of the waves, and the atmosphere attenuates and smears each individual wave the maximum amount. Over 40 years of history, it kind of culminates down to we began to understand the phenomena better. We could predict it better by using better tools. We could predict it faster by using faster computers. And we had design systems which could iterate through hundreds and thousands of designs very quickly to look for ones that were successful. None of that would have been successful at all without some really clever, innovative thinking along the way that got us to the point where we could address not just shockwave pressure, but looking at a solution that just gave us the minimum noise that we needed. So if you look down on the bottom there's a scale of perceived level in decibels. That's one acoustic measure. A little bit different from the A-weighted sound level that you see a lot of things like weed whackers noise measured with. But anyway, it's just a measure of sound. Concorde's sonic boom level was up around 105 dB. We're talking about something in the 70 to 75 range. So a tremendous reduction in acoustic energy in the sound. And essentially not a sonic boom, but a soft sonic thump, kind of like a car door slamming across the street. So we feel a change that's remarkable enough to get us close to where acceptable flight is something that could be considered, or get us to where that point. So we didn't start out just to create an X-plane and go fly and do something cool. But as these new approaches to reducing sonic boom noise got further and further developed, we started to think that maybe it would be possible to design an airliner that could include these technologies. So that's where we started. Conceptual design study, which incorporated this technology, but also looked at all of the things that make an airplane an airplane, not just sonic boom noise, but takeoff and landing noise, high altitude emissions, fuel burn, operations, and above all, reducing sonic boom. And if you look down on your left, you see the classic plot of pressure versus time. And we all look at most supersonic aircraft. We call it an N wave because of the two pressure pulses and the expansion in between them. Make it look like a lot like an N. But you can see where we can get to with a signal that's almost more like a sine wave. and you know that that's going to be producing a lot less noise. We validated these designs by doing wind tunnel tests where we measured the pressure near field, close to the airplane, in what we call the near field. And we felt that, well, you can see on the lower right, our predictions matched, our measurements matched our predictions extremely well. And this really was the first time ever that you saw that there was a way forward to designing an airplane that was a real airplane, but was also quiet at supersonic speeds. So really a breakthrough. Lockheed and Boeing were our industry partners on this effort, and their designs are represented there. And if you look at those two designs, they have three common features. One is that the whole airplane is shaped in a way that contributes to this creating this desired shockwave pattern. So it's a very integrated 3D design. One of the things that's really hardest to deal with is the shock wave associated with slowing the air down to get it into the engine, so you have to kind of hide that in some way. Mounting the engines on top is one approach, but there are other approaches that work as well. The Lockheed design on the right actually it's a 3-engine airplane, so it has 2 below and 1 above. And then some sort of unique empennage, because the last challenge really to be solved is at the back end of the airplane where you've got propulsion shocks and tail shocks and the closeout of the airplane all interacting. Being able to essentially design a shockwave system that gave you the desired signal on the ground was the real challenge. So the empennage, the tail of the airplane, is going to be unique in terms of how it carries lift to the back of the airplane. So keep those 3 features in mind. You'll see them again later. So why do we think it's quiet enough? Again, lots of dedicated research over many years to pick apart the sound of a sonic boom and really understand why it's annoying to people. And that's an important point, is if you look back on the days of leading up to the ban on supersonic flight, and even since then, there has been a lot of research, a lot of concerns about sonic boom that have been alleviated through research. In the beginning, it could have caused earthquakes. One of the first interests from the Air Force was, would 2 supersonic airplanes flying in formation, would the shock waves from one send the other spinning out of control? So each of these things was examined, and it really came down to, in terms of wide acceptance of supersonic flight, the most important thing was to identify what causes the negative human response, particularly for sounds heard indoors. So we started out with laboratory tests. Our original boom box is not on this chart, but it was a little concrete booth with a door full of speakers, and people sat in there and listened to different sounds. We eventually created the interior effects room, which is shown on your left there. It looks like a living room, feels like a living room, but it's got a great sound system that essentially can reproduce the sounds of sonic booms as you hear them indoors. Again, the laboratory environment is great because it's repeatable. And you can create a lot of variation in the sound, but despite the fact that it looks like a living room, it's not your living room, so your reaction is different. So our next opportunity was to get out more into the field and try to understand how these sounds are perceived in other environments. We actually invented a maneuver using a conventional airplane where you dive steeply and go supersonic briefly, and you kind of generate a pulse of sonic boom that travels a very long distance before it reaches the ground. And doing so, it kind of gets some of those features in terms of rounding and low delta pressure that are features of a quiet sonic boom. And it's repeatable and variable by where you do the dive maneuver relative to the community that you're testing in. And that's where my 30 seconds of supersonic flight time came in. I got to do that maneuver once. I can't do the pilot stuff. You got to roll inverted and dive steeply and roll upright. It was cool. But we were able to do, so the problem is it does create this quiet sound in one location, but in other locations it creates a very loud, focused sonic boom sound. So you can only do this type of testing in very limited environments. Edwards Air Force Base and their housing area is a great example because it's a little housing area kind of in the middle of nowhere, for those of you who have been there. So that was an opportunity to learn. Most recently, in 2018, we got a little more daring and wanted to expand, not necessarily our knowledge of how people responded to the sound of the boom, but how to do a test in a community. So we were able to find a community which was relatively isolated, and by being close to the water, Galveston, Texas gave us a place to do the dive maneuver, put the loud sounds, but give us a chance to go out and plan the test, develop a survey, get survey participants, perform measurements in the community, do the flight operations. So really put together a lot of the pieces that we think are going to be necessary to get the data that we really want. So as you can see, we're ready, after years of work, we're ready to take that next step with flight testing over large communities. So the goal of the mission is, again, it's all about data. We'll talk about the airplane in a minute, but if I could have flown a brick and gotten the right sound, that would have been okay. But the goal is to define response to these sounds heard in communities at an international scale. So we're talking about large populations with hundreds, tens of thousands to hundreds of thousands of survey responses, varied communities in terms of demographics, geography, climate. Multiple locations, important, ideally, not just in the U.S., but internationally. You have to be able to create a range of sound levels, possibly including normal booms if we really want to get a noise response. 6 to 8 exposures per day is kind of what we think, at least for a long time into the future of the future of supersonic flight, any community might experience. You have to test for long enough so you really begin to understand how people react to repeated exposure, and again, get the international community involved, because eventually this is going to be presented to the international community, and we want to make sure they understand how we're collecting our data, so they're ready to receive it. So to do that, community overflight with an aircraft that produces a representative sound was viewed as the best way to do this. So we had design potential, we had a need, and that really essentially came together to the Quesst mission. And the idea, again, is those requirements drove us to, can we take what we learned about these low sonic boom designs and create something that we can use to do this data? So the most important thing is this is a prototype, it's a research airplane, but the sound has to be representative of the sound of supersonic airplanes in the future, and you have to do it in a way that you can't do a dive maneuver, for instance. You have to really do it in a way that's operationally similar to the way supersonic aircraft fly. So we are using a new design airplane, the X-59, to gather data on this community response. And the mission's in 3 phases. They're all active right now. The focus right now is building the airplane, design it, fabricate it, ground checkouts, flight envelope clearance, prove that the airplane is safe and ready to fly. Next step would be to collect data on the acoustic performance. Are we getting the signal that we expected, and is it predictable as we expected, and does it vary as we expected? Once we're sure of that, we're ready to take the final step and go out into the community and perform a series of community tests, which include overflights, sound measurements, and surveys of people's responses. A few words about the airplane. It's an X-plane. Again, we all do tests, so we know that the X-plane ideal is to define a problem, minimize the number of requirements, and create a system that meets those requirements effectively. And the X-59 does that. The shape is new and unique, and you'll notice that the long tapered nose, the 3D shaping, the unique propulsion installation, and the unique empennage. We have every kind of tail surface imaginable. Again, that was just because what would work, but all those features that will be in a future supersonic airliner, or may be in a future supersonic airliner, are in the X-59. Other than that, it's pretty much try to put it together with conventional construction techniques and using as many parts that already exist as we can find. So without going into all the details, a current engine, lots of legacy systems from existing airplanes, and uniquely you'll notice there's no window on the front. So one of the new systems that we brought into is an external vision system, which allows us to fully shape the airplane, but still provide the pilot with sufficient visibility for normal operations. It's 100 feet long, 38 feet of his nose. Speed is Mach 1.4. That was just a fallout of where we could get to with an existing engine. Sufficiently supersonic that we don't have to worry about some of the transonic effects. But fast enough for the purposes of getting the data that we need for supersonic operations. We'll fly at an altitude typical for supersonic flight of 55,000 feet. So very excited to see this airplane starting to come together. It's all the responsibility of a great team. Lockheed Martin is our prime contractor. They're leading the design, fabrication, integration, and test. They have a lot of subcontract partners, over 50 companies from around the world, bringing their expertise to bear on building and integrating components. NASA's role is to provide some key systems, notably that external vision system that I talked about, and the flight test instrumentation system, which will measure a lot of the parameters of the airplane during the Phase 1 flight testing. All the components that came from donor aircraft, NASA was responsible for going out to all the aircraft junkyards and collecting all that stuff and bringing it all to Lockheed. And also the ground servicing equipment, everything we're going to need to support the airplane while Lockheed is testing it and while NASA is operating it. So I have to say the effort has experienced any manner of problems, including the COVID crisis, and the team has really come together. And for a contractor, integrator perspective, the two teams are really working very well together and depend on each other. So where are we? We've almost got a complete airplane. As a matter of fact, we do have a complete airplane now. It's the assembly was completed just a few weeks ago with the installation of the empennage, which is essentially the lower engine mount plus the horizontal stabilizer. You can see it there in the middle picture. And everything else, the nose, everything is on the airplane except for some external panels. We completed structural testing a year ago in Fort Worth. We actually moved the airplane on a truck to Fort Worth from Palmdale, did the testing and moved it back and safely. And now we're in the powered system checkout phase. Trying to work through making sure everything is functioning independently so we can end production, move the airplane out to the flight line, begin the final integrated tests, engine runs, taxi, and leading up to first flight, hopefully sometime by the end of this year or early next year. So that's Phase 1. Phase 2 has a lot of pieces. This is where my role as Mission Integration Manager really comes into play because I have to make sure that all these different activities stay on track, stay focused on delivering what they need to do this acoustic validation. So a big part of this is prediction. Again, we have to be able to accurately predict all that system of shock waves near the airplane, and then actually propagate that signal to the ground and calculate what the noise level, what the noise exposure is on the ground. So the prediction is an important part of the design, but it will be a very important part of the community testing because on any given day where we want to produce a loudness level of X, we have to need to know how to fly the airplane to produce that level. So again, the speed and accuracy of these codes is kind of the core that got us to the point where we could do these designs, and that effort has even gone beyond where we were originally as we add more and more detail into the actual design of an airplane with antennas and environmental control system ducting and a real propulsion system. The capability kept improving, the speed kept improving. Looking at the uncertainty of the results is also an important piece, so the ability to do that. And then, like I say, integrating it all into a tool that can predict your trajectory and your aircraft configuration that you need on a particular day of flight. So that's the prediction side. We've got a good predictions in hand. We want to validate those tools. We want to make sure we're getting the right signal. So we're going to do this acoustic validation testing in the desert, out around Edwards Air Force Base and NASA Armstrong. Measurements of the pressure signal near the airplane and measurements of the pressure signal just above the Earth's boundary layer and measurements of the pressure and the noise on the ground. These are all things that NASA has done in the past. We have these capabilities, but we've never done it with on such a signal that's such a low intensity signal, and we've never done it on the scale that we're talking about. So we're developing new versions of capabilities that we've already had to prepare us for this acoustic validation. So to measure the signal near the airplane, we actually fly two aircraft in formation, the X-59 and a test aircraft with a probe on it that probes in and out and measures the shockwave data. We do that on one of our F-15 research aircraft that we have at NASA Armstrong. And again, you're looking at the near field signal on the right, and you can see the difference between what would be a typical supersonic fighter and how small the pressure changes are on the X-59 design. Again, for the ground, we've done lots of ground measurements of sonic boom signals, never to this scale. That's a map. That little tiny light spot in the middle is Rogers Dry Lake, so you can see the scale, and we're laying out an array that's about 30 miles wide. We need it to be autonomous. We need to be able to measure signals and extract signals from noisy environments. So we're building a new set of ground recorders. Eventually we'll get about 100 of them, which will be used not only in phase 2, but will be used in the actual phase 3 community testing as well. And a plan to do this all safely and efficiently and adaptable to changes in weather, aircraft availability, et cetera. So a big part of getting ready, and again, this will all start once the airplane has completed its envelope expansion and is ready to fly in the test ranges. Which gets us to the payoff, the community testing. 4 to 6 tests are planned, starting in 2025. The first test is going to be, we're going to make it a little bit easier on ourselves. We'll fly from NASA Armstrong so we can return to our main base every day. The next up to 5 tests will be deployed. There's all kinds of activities that are kind of already in work. They're all listed here. I won't go through them, but selecting a test site. Very important. I mean, you'd love to be able to fly anywhere, but since it is an X-plane, there are some operational limits that are placed on it in terms of the airfields and things like that, and the airfield capability that it needs. So we're kind of picking an airfield, and we're trying to identify as many airfields as possible, and then be able to pick randomly from communities around those airfields to identify where we're actually going to fly for our testing. Survey design, recruitment, statistical methods to analyze the data, exposure design. Again, we don't want one level, but we want a multitude of levels repeated in a way that gives us a good representation of dose that we can measure response to. And then taking that information, developing the dose-response relationship, and as I say, leading ICAO along the way to the point where we're ready to where they can take this data and use it for the purposes of setting a standard. Speaking of ICAO, a little bit about them. The International Civil Aviation Organization Committee on Aviation and Environmental Protection. So ICAO is a UN body responsible for making worldwide air travel a possibility. Aviation and environmental protection is obvious. Noise emissions from aircraft. They develop what they call SARPs, standards and recommended practices for protecting the environment. In general, the SARP consists of a measure, something that you want to, some metric that you want to control, a procedure so that everybody can test and create a value for that metric in a consistent manner, and a limit. CAEP meets in 3-year cycles, so any decisions are at the full that are to be taken are taken at the full CAEP meeting. The next 3 years, work goes on somewhat independently, and then more information is brought forward to the CAEP meeting for decisions. We've been at this for quite some time with them. Started the CAEP 10 cycle in 2013. We actually got to the point where CAEP went from observing and reporting on activities in supersonic flight to actively pursuing the development of an en route noise standard. And NASA and the data that we developed has been a part of that development since the beginning. Initially, we focused on what metrics. I mentioned perceived level as a possible metric. That's a metric that's very correlatable to human response for sonic boom sounds. When we get to these kind of thump sounds, there are other metrics which perform equally well. So we haven't made it. We have candidates, but we haven't made a final decision on what the metric will be. Procedures. This process of collecting data or doing analysis, collecting ground data is very similar to what will eventually be done in the certification procedure. So knowledge that we gain in this is very applicable to the CAEP's effort to develop procedures. And then with the community response data, again, it's not NASA's job to establish limits, but it gives the CAEP the ability to understand response and set reasonable limits. So the current goal, which I have to say is in jeopardy due to some of the delays that we've had, was to bring this standard forward to the full committee to the CAEP meeting in 2028. So the idea was for NASA to provide the data a year prior to the CAEP meeting in 2027. So like I said, we're getting close to that, and we'll probably, we're thinking about the best way to move forward in terms of when to bring the standard forward. So just briefly, I've talked a lot about data, prediction data, acoustic measurement data, response data, all of it, many sources of data, and many challenges that we're looking at, including understanding the uncertainty of the data, how to analyze it, how to identify. Really, one of the big problems is, given this broad community and the natural kind of some variation in sound level that might be experienced, how do you associate one individual survey respondent's response to a sound level that they heard? Ensuring representativeness. I mentioned ideally to get a representative data set, you randomly sample people. We can't do that because we're restricted by how we can fly the airplane. So building from the constraints that we have and understanding how to get as representative a data set as we possibly can is one of our key efforts right now. Without creating a situation like some of the previous sonic boom tests where people really got disturbed, how do you generate sufficiently loud responses to fill in the top of that highly annoyed response curve? Similar studies for noise exposure, particularly from airplanes, have shown high variability from test site to test site. We only have a limited budget to do testing. 5 to 6 tests is a small amount. So how do we handle the possibility of high variability between test sites? One of the things we're really concerned about is introducing bias into the results. NASA has a very good name and a very good reputation. So we really kind of want to disassociate NASA from the testing. That's really hard to do because we also have a really good PR department that loves to let everybody know what we're doing. So again, how to inform the community, because you can't just start testing because it is a new, unique sound, and if you just introduce it without people being able to get some information, you're going to get potentially bias in the wrong direction, but not create too much of an interest in a future that we're really not ready to predict yet, but we're just trying to get data that gives us that gets the public's impression into the rulemaking process. And of course, data handling, processing, and more security of that data are all things that we're working with in our preparations for our community testing. So with that, I hope you've enjoyed this presentation on the Quesst mission. Again, the whole idea of the mission is solve the technical and regulatory barriers to quiet supersonic flight over land. And NASA has made a commitment to the international community to provide data to do that. Development of an X-plane of the X-59 is core to this effort. Great team, and an airplane product that is coming along slowly, but coming along. As is the preparation for acoustic validation and community testing. Can't emphasize enough that really our focus and why it's maybe taken longer to get the airplane ready than we thought is this is going to be a very unique X-plane in that it's not just going to be in test ranges. It's going to fly in the national airspace system over large populations of people. So we need an airplane that's safe and reliable and ready to do the mission. We'll work with FAA and ICAO on the development of our standard, and we're looking for input from this community and the international community to help make the mission successful. Maybe a cool airplane, but it's really all about the data. Thank you very much for your attention. Please attend session 2A today, where you hear more about our preparations for our community testing from some of my colleagues. And if you want more information about the mission, there's our website. Thank you very much.